Good afternoon, everyone. I'm Zeng from the National University of Singapore. It's my pleasure to present our recent work, ShadeWatcher, recommendation-guided cyber threat analysis using system audit records. This is a joint work with Xiang, Jiahao, Yinfang, my advisor Zhenkai, Tat-Seng, and Zheng. Recently, we have been witnessing a rapid escalation of cyber threats that intentionally target large organizations. While performing these attacks, attackers inevitably leave footprints in the victim systems. A common question faced by security analysts is how to combat these cyber threats using attackers' footprints. Audio records are a common footprint, which proves to be a valuable data source for analyzing cyber threat. They can provide a low-level view into a system by monitoring system entity interactions. For example, when an attacker exfiltrates sensitive data, the password file, his activities will be recorded as system calls in the audio records. To facilitate attack detection and investigation, audio records are usually navigated through a provenance graph that describes the system's historical contexts. Here, by following the data provenance, we can find that the password file is leaked to a remote server through malicious executables. In general, system auditing connects separate attack steps, presenting the overall attack scenarios for security analysts. Based on how audio records are used for cyber threat analysis, existing work can be categorized into three directions. Statistics-based approaches quantify audio records' degrees of suspicion by their historical frequency. However, the primary concern for this line of research is the number of false positives generated by rare but benign system activities. Specification-based approaches can maintain a low false positive rate by mapping audio records against the knowledge base of security policies. However, such security policies are usually time-consuming and error-prone to develop because they heavily depend on expert knowledge. Learning-based approaches typically train a model of benign behaviors and then detect deviations as cyber attacks. Unfortunately, current learning-based approaches only produce detection signals at a call screen level, specifically behavior level, which requires intensive manual efforts to review individual audio records in behaviors for attack investigation. In this work, we aim to address these limitations. Our solution is based on the observation that cyber threats can be revealed by determining how likely a system entity would interact with another system entity. In particular, unlikely or unintended system entity interactions would reveal cyber threats. For example, sensitive files normally do not interact with the public networks, which otherwise indicate the data exfiltration activity. Such likelihood can be estimated using historical system entity interactions. For example, if we observe that this GT cache process has interact with the process status file, then it's reasonable for this process to communicate or access another process data file. This problem is similar to a recommendation task, where the primary goal is to determine how likely a user would interact with an item. Earlier recommendation systems comprehend user preferences by finding similar users using historical user item interactions. To illustrate this idea, we use a movie recommendation scenario, where Alice is a target user for recommendation. Since both Alice and Bob have watched Iron Man, recommendation systems would consider these two users similar. And because Thor is Bob's favorite movie, recommendation systems would also recommend Thor to Alice because she is similar to Bob. Unfortunately, user item interactions are insufficient to recommend items that are disconnected in historical interactions. For example, the Avengers here. To address this issue, modern recommendation systems would adopt item side information to form a high-order connectivity that links the similar items. Here, because the Iron Man and the Avengers are connected through multi-hop passes based on Action and the Marvel Studios, modern recommendation systems would recommend the Alice to the Avengers because it's similar to Iron Man. The Little Woman would not be recommended because it's disconnected to Alice. Inspired by recommendations, we make an observation that similar system entities in audio records would share preferences on interactions. For example, sensitive data do not like interacting with the public networks. And to uncover system entities' similarities, we aim to identify high-order connectivity based on side information of system entities. For example, if we observe that two process status files were correlated through process status information, then we would determine that they are similar and share the preferences of interacting with the GTCache process. As a result, we can formulate a cyber threat analysis in audio records as a recommendation task, which models how likely a system entity would prefer its interactive entities. To perform recommendations on audio records, we propose ShadeWatcher. It takes the system records as input, and then generate a knowledge graph. And based on this knowledge graph, ShadeWatcher will train a recommendation model to recommend the adversarial system entity interactions to security analysts. First, given audio records on a host, we parse them into a provenance graph, where the nodes in the graph are system entities, for example, a process, a file, or a circuit. And the edges denote the system cores. We consider that two system entities are interacted as long as there is a path that links these two system entities in a provenance graph. And here, we extract all the system entities into a bipartite graph. While system entities' side information plays an important role in uncovering their semantics, such information is not encoded in a provenance graph or bipartite graph. However, a recent study has shown that such side information can be inferred from the context in which system entities are used. As a result, to incorporate high-order connectivity as in recommendations, we combine system entity contexts that represent the side information and the system entity interactions into a knowledge graph. In this work, we represent a knowledge graph as a set of triples. Each triple consists of three elements: a head, a relation, and a tail. Head and the tail here represent the system entities, and the relation denotes the system core or interactions. Taking the knowledge graph as input, our key idea is to use different order connectivities in the graph to model the likelihood of system entity interactions. Towards this end, we first model first-order connectivity to parameterize system entities as embeddings. Then, we try to model higher-order connectivity by propagating embeddings from neighbors via a graph neural network. At last, we classify system entity interactions into normal and anomalous. In what follows, I will elaborate on these phases. By modeling first-hop connections or first-order connectivity in a knowledge graph, we aim to map system entities into a vector space to preserve their semantics. Our intuition is to use the system context to decide the semantics of system entities. To do so, we use a knowledge graph embedding method trans R. At its core is to use head plus relation to define tail in knowledge graphs tables. It's worth mentioning that trans R will assign distinct semantics of individual system entities conditioned on different relations. For example, if this GT cache is used on the write and unlink relation context, it will be given two different embeddings, which indicates different semantics. Beyond the first hop connections, multi-hop passes are inherent in a knowledge graph. Such high-order connectivity not only supplements similarities among system entities, but also exhibit how system entities influence each other. The left two-hop pass shows the similarity between two process data files because they both interact with the GT process. The right three-hop pass describes how the password file is transmitted out of an enterprise. To model such high-order connectivity, we adopt a graph neural network to iteratively propagate information along with the multi-hop passes in a knowledge graph. Afterward, we aggregate the embeddings from all the propagation iterations to form the final system entity semantics. After obtaining system entity embeddings, we apply inner product on them to predict how likely a system entity would not interact with another entity. If the likelihood is beyond our predefined threshold, we would classify the interaction as a potential cyber threat. To keep up with the evolving system entity interactions, we also enable dynamic updates of our recommendation model using analyst feedback on detection signals. The details of such a model update can be found in our paper. To evaluate ShadeWatcher, we use 6 real-world cyber attacks simulated in a testbed environment, and 4 APT attacks from the DARPA Transparent Computing TC dataset. We focus on evaluating the following aspects. How effective is ShadeWatcher as a threat detection signal? To what extent do different order information facilitate cyber threat analysis? And how efficient is ShadeWatcher in deployment? In terms of ShadeWatcher's effectiveness in cyber threat detection, we aim to identify cyber threats based on system entity interactions in the DARPA TC dataset and the simulated dataset. The DARPA TC dataset has over 68,000 malicious interactions and around 8 million benign interactions. Our experiment result shows that ShadeWatcher only misses 10 malicious interactions, and its overall false positive rate is well below 1%. As for the simulated dataset, it consists of 39 malicious interactions, 2 of which are missed by the ShadeWatcher. From this table, we can see that ShadeWatcher can distinguish benign and malicious interactions with a high accuracy. To answer how different order connectivity facilitates cyber threat analysis, we compare different knowledge graph embedding algorithms and study the importance of high-order information propagated by our graph neural networks. The results are summarized in this table. The combination of trans-R plus graph neural network represent our ShadeWatcher. Compared with one-hot encoding, trans-E and trans-H, trans-R's advantage is to distinguish the semantics of system entities conditioned on different relations. We observe that ShadeWatcher achieves the best performance in terms of the AUC values, which implies that high-order information is beneficial for cyber threat analysis. And it's important to distinguish different semantics for system entities under different relation contexts. We measure ShadeWatcher's runtime overhead on the public DARPA TC dataset at different phases. We perform all experiments 5 times and report the mean results in this table. From the table, we can see that ShadeWatcher can pinpoint cyber threats from nearly 1 million system entity interactions within several seconds. We would like to point out that we obtain these results by running ShadeWatcher on a GPU machine. By further evaluating ShadeWatcher on CPU machines, we observe that ShadeWatcher can still finish system entity interaction classification within 4 minutes, which is still practical in real-world scenarios. To conclude, nowadays cyber threats are everywhere, leaving traces of shades in the victim systems. To reveal these shades, we propose ShadeWatcher to analyze cyber threats through recommendations on system entity interactions. It models a system entity's preferences on its interactive entities. Our key insights are that similar system entities would share preferences on interactions, and higher order information can better correlate similar system entities, even though they are disconnected in a preference graph. Thank you for your time and attention. I'm happy to take any question.
Thank you very much for the presentation. I am going to coordinate the Q&A. We have time for a few questions. I'm keeping an eye also in the online platform from our audience that is following us from home. If you have any question, could you walk to the microphone? Yeah. Can we turn on the microphone for the Q&A? I mean, for the sake of simplicity, I'm going to give my mic.
Thank you. It's a very interesting talk. My question is simple. I noticed that the false positive rate is low, 0.33%. It's a great. But with given 8 million interactions, still this is a big number. Is this manageable? We're talking about 10,000 false positives in absolute numbers. So are you satisfied with this? How can we do better?
Okay, thanks for the question. So first of all, I need to acknowledge that, like most anomaly detectors, ShadeWatcher inherits the limitation of a high false positive rate because it detects anomalous system entity interactions as cyber threats. And so first of all, ShadeWatcher is used to perform the cyber threat analysis and produce the detection signals for security analysts. And if the security analyst finds that the false positives are too many to analyze, we suggest the security analyst to use further technologies, for example, the threat alert train engine systems to rank all of these malicious system entity interactions so that analysts can focus on the most important ones. And I believe this is an open question for all of the cyber threat detection systems. And we also will focus on solving or mitigating this type of question in our future work. Thanks.
Do we have other questions from the audience? I just have a small curiosity, do you feel that this recommendation system principles could be extended also to other domains such as in code analysis? Or do you think that these principles apply only to the audit logs? Like this relationship between the recommendation systems, information propagation that you used here, and other domains such as program analysis and code analysis, maybe for malware detection?
Yeah. So yeah, that's a very good question. So to my knowledge, or to our knowledge, we are the first to use recommendation engines for the cyber threat analysis. And this is because we find that the information propagation in a knowledge graph or in a provenance graph built upon audio records are quite important to detect cyber threats. So we believe that recommendation systems or recommendation engines can be possible future directions for other security fields. For example, the source code analysis and the binary analysis. Because in source code or program analysis, because in program analysis, we sometimes will construct a graph, for example, control flow graph or code property graph out of programs. And since the information propagation is also important in program analysis, maybe we can use this recommendation engine as a searching engine to find interesting interactions or activities for us to analyze some malicious activities.
Thank you.
Thanks.
Let's have another round of applause for our speaker.